Hello guys, this is Tanajian and welcome to my channel. In today's video, we're going to discuss about a magnificent phenomena because of which you're alive on Earth today, because of which the core of the Earth is still hot, because of which three physicists, John Martinis, John Clarke and Michel Devoret, got Nobel Prize in Physics this year. You guessed it right. The phenomena is quantum tunneling. Quantum tunneling is so magnificent that if we become more advanced in the following topic or phenomena, then we could just throw a ball through the wall without either breaking the ball or the wall, and the ball just passes through it. So let's get started.
The Nobel Prize in Physics for 2025.
Nobel Prize in Physics.
This year's prize is about encountering quantum mechanics on a new scale.
Before starting with the main topic, quantum tunneling, we need to understand some basic terms of quantum mechanics and then what are the basic principles of quantum mechanics before understanding it. So let's get started. What are the basic principles of quantum mechanics? Now, number one I would like to say is de Broglie. Yeah, it is de Broglie, not de Broglie. De Broglie's equation, which he gave around 1923 to 24. The equation states that lambda is equals to h by e. Here, lambda is wavelength. I hope you know what is a wavelength. A wavelength is the distance between two crests, two draws and two crests. Two crests and two draws, which means, if you want to know in the layman term, two hills and two valleys. Yeah. So like this is one wavelength, this is another wavelength. I'm gonna write it down. Wavelength. The other thing, h. H here is Planck's constant, which, if you want to remember, has a value of 6.626 times 10 to the power minus 34 joules second. And momentum, you must have studied in your lower grades, is nothing but the product of mass into velocity. So this is de Broglie's equation, which he gave. You know what is significant of this equation? That it links between two things in quantum mechanics: waves and particles. This equation is a link of both those quantities. So if I have to explain you guys what this equation means, for example, if a particle has a following momentum, then it must have this much wavelength. Now if I am moving, I must be emitting I must be in the form of waves. Like, I'm not emitting, but I am the wave. But I am, my waveform is not that visible, because if you see, my mass is high enough and my velocity is low. We don't care about that, but my mass is high enough, so dividing by something big will make it more small. And guess what is in the numerator? A very, very small quantity. To neutralize this, we need a very small quantity in the denominator too. And that is why very small mass, like almost mass, like electrons can be here. So electron has a mass of 10 to the power minus 31, like 9 times 10 to the power minus 31 kg. So this would almost create a gap of 10 to the power minus 3 meters, which is actually a nice amount of wavelength to be detected by our instruments. But if I put any average human with mass 100 kg, then we would have a problem because the wavelength would be only 10 to the 6.626 times 10 to the power minus 32. The velocity is 1 meter per second. So that is so small, so faint that we could not detect it. That is why our waveform is not visible. In a discussion on this, the next topic after this is Young's double-slit experiment. So let me just clean the board. So after the 17th century, like the Newtonian era. So like if I have to briefly explain the different eras. So we have the first Galilean era, I guess 1300 or 1200 maybe. Write down in the comments, I have forgot about that. But the Newtonian era is 17th century, where he discovered a lot of brilliant things: motion, force, gravity, optics, invented calculus, and then he spent his life in alchemy. That's different, but yeah, the 17th century is the Newtonian era, and Newton had given a particle format of light. That light is a particle or a wave, and then it is challenging Newton was a big deal because he was a big name, so challenging him would be quite difficult. So Young, a physicist, performed an experiment to challenge him that light is a wave. So there, that time there had been discussions and debates that if light is a particle or a wave. Newton and some other scientists said that it is a particle, and then some other scientists like Thomas Young said it was wave. But then we figure out in the 20th century that light is neither a wave nor a particle, but it follows a dual nature of both. So let us see the experiment. So here we have our source, where we emit the laser or light source. Here we have the slit, and then here is the screen. Okay. So if light was a particle, then it would travel like this. Okay. And then if you cluster around somewhere here, and then you would see a pattern like this. Two spikes in the graph. But when Thomas Young performed the same experiment, what he saw was astounding. He found out that the pattern formed is this. In short, we call this interference pattern. Here we have the nodes, or the white area, or the light area. Here we have the antinodes, or the dark area. So let me explain the concept behind this. So for example, you have two waves. One is this wave, second is the other wave with the same direction. When they merge, okay, they create a larger wave. This is known as constructive interference. Now, if you just change the direction, not direction but the sign of amplitude to be negative, so now it becomes like this. Sorry. Now this, if you combine, you get nothing. Because this is known as destructive interference. Constructive interference, destructive interference. So this spikes are the region where they constructive interfere, the waves, and then the part here is the place where they destructively interfere. So we get nothing, dark spot or black area. So this means that light is a wave, so it is traveling like this. Here it happens like this. And you can see that now light destructively, they interfere destructively and constructively, giving this pattern. Now, after 150 years, I guess, the scientists tried to put observer here. Observer. Okay. same light was emitted, but instead of this wave pattern, you would be surprised to see that what they observed. They had observed that after putting some detectors or observer, we are getting particle nature of light. Like the light shows the nature of a particle, and that is why we get two spikes. Now, this is where the probabilistic nature of quantum mechanics comes in, and this is where there is a huge debate and discussion between Niels Bohr and Albert Einstein, where Albert Einstein says God doesn't play dice with us, against this probability theory of quantum mechanics, because here it mentions that light is both a wave and particle, and then when we observe it, it is a particle. When we don't observe it, it's a wave nature. This is completely hilarious because observation changes effect. So Einstein said this sentence, and the sentence Niels Bohr said is, "Do not tell God what to do with his dice." Oh my god, the sentence is so deep and then beautiful. So let's come back to topic. The third concept is Heisenberg's uncertainty principle. Okay. This principle basically states that you cannot measure the momentum and position of an object together precisely. So, if you have delta x, delta p is greater than or equals to h by 4 pi. Now, what is delta x? Delta is not change, as we learned in our 11th derivatives. Here, the first chapter of 11th grade, if you learn in your CBSE curriculum NCERT, that first chapter, the units and measurement, you'll learn that delta stands for error. Error in position and error in momentum. So if our detectors are so nice that they can reduce the errors in position, we can finally find out the position of the object. Then, according to the principle, its momentum should increase. The error in momentum should increase. Then we cannot measure its momentum. So the best example of this is using cameras. If you have a high frame capturing camera, then you will get, for example, the ball is traveling in a trajectory. Then if you have a high frame capturing camera, then you will see this image of the ball. But then if you want to, here you would know the ball is at this position, and then if you capture at this position, you will notice it is in this position, but you won't know where it is going. You can go here, 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 here. But if you can calculate, tell where is it going, then you won't know where its position, because you will see that it is trying to go this way, but the position can be anywhere here. This is the principle of Heisenberg's uncertainty principle, which basically, again, if I quoted, that error in position and error in momentum are inversely proportional, which means more we get precise in a particular unit, like position, then the other unit gets more uncertain. We have many other examples. This is one of the examples. We have energy and time, I guess, and then we have many more examples where there is uncertainty between two quantities, physical quantities. One of the examples is this: momentum and distance or position. So I hope you have understood the basic of the quantum mechanics, and people who know it can skip to this part. Now I have already mentioned the time stamp in this at the introduction of the video. So now we'll discuss about what is quantum tunneling, the most exciting part of the video. Now let us begin to the introduction of the topic quantum tunneling. So for that, we need to know that this is a fixed surface. surface that does not move, it's fixed. Now if you have a wave traveling and hitting this surface, after hitting, the thing you will get is, let me just make it here. This. Quite opposite to this, because here we have, you can see this. So the amplitude turns around like this and travels in the opposite direction. Let me mark the direction of the velocity of the wave. But here, as you can see, there will be a tiny amount of wave travel like this with a velocity v dash. So now you can see that how in the world did the wave form of particle escape the barrier, because we have learned that a particle is a wave and particle. So if this has happened, that means that some amount of particles got escaped through a barrier. Like how? So the correct explanation to this is the principle which I've taught you some while ago. Correct. Heisenberg's uncertainty principle. So, for example, let me show you like here. As I've told you that this is a particle. Now according to the principle, the particle is here, here, here at the same time. It can be anywhere here. We don't know. And then now, if you are here, particle is here and here. The probability of being here was 1/3, 1/3, 1/3. Now, if someone is here, the particle can be here and here. Even though the probability of a particle being here is so minuscule to be considered impossible, that is why we don't see any effects of quantum tunneling in our present day everyday life. This have like almost 90%, more than 90, actually more than 99% of chance. This is less than 1%. But that 1% causes quantum tunneling. You explain using a probabilistic graph. So if you know what is a probabilistic graph in quantum physics, you know what is a wave function. As I told you, quantum physics is based on probability. Wave function. This is psi, the symbol of wave function. This indicates the function that takes inputs of a normal features of a particle, momentum, velocity, and releases in a form for waves, momentum of a wave, velocity of a wave, etc. So this is nothing but converting, this is nothing but storing information about the wave, basically. And then if you take the same function, taking a modular square of it, you get the probability of the wave being at a particular place. That is why the Schrodinger's equation, if you see, explains something about the energy efficiency equation. It is similar to the conservation of energy equation. If you want, I can make a very detailed video on it sometime after. So if you want, please mention in the comment section. Yeah, so like basically this symbol tells about the probability of electrons in a particular cloud, because in quantum mechanics we don't have orbits, we have clouds of electrons. Electron can be here, anywhere. So the probability of electrons being at this point, and this point, and this point, this is quantum mechanics. So we can explain it using a barrier, like the thing we have explained before, but with two barriers. A box. Now, probability graph of electron. For example, this is the electron orbital cloud. Now, this is the probability graph of it. Now, this means the highest probability. This means the lowest probability. But outside the box, the probability is not zero. It is minuscule, but not zero. So, at that probability, quantum tunneling happens. I hope you have understood the basics behind quantum tunneling. Now we'll discuss about the links between quantum mechanics and radioactivity. In the starting of the video, I've told you about that quantum tunneling is so important to keep the core of Earth alive or heated, because Earth's core is warm due to the radioactive decay of certain radioactive elements like uranium, radon. Radon is a radioactive gas, noble gas. Radium, thorium, potassium, second actinide, uranium, neptunium, plutonium, whatnot. So, how is quantum tunneling linked to radioactivity? The best and the easiest explanation, I guess I can tell you, is using a potential well concept. But before that, let me explain you what is radioactivity. This is a nuclei. It is heavy. It's electrons. We care only about the nuclei. It is a heavy nuclei. It's so heavy that it cannot do anything if it is not stable. So it releases an alpha particle. Alpha particle in the sense 2 protons, 2 neutrons, helium 2 plus nuclei. Helium 2 plus atom, or the nuclei of a helium atom. So this is known as alpha decay. Now, what is the relation between alpha decay and quantum tunneling? Let us draw the potential graph I was talking about. Okay. Now, let me just make this straight and a little bit of steep here. Okay. Now, if I have a ball here, and if I let us take at the base of the ground here. For example, if I need 10 units of energy to escape here and to reach this point, we need 10 units of energy to reach at this point to escape this pit. If I apply it as 4 units of energy, will it escape the pit? No, right? So let me explain you what is alpha decay is energy required. Do you know about something known as gravitational potential energy? Let me just explain it here. I erase it later. What the gravitational potential energy is minus g/m by r. Let me just put some sips of water. I am tired. Thank you. Yeah. So, for charges, Coulomb's law, if you take this is from the Fg is equals to gm1 m2 by r square, or capital M small m. Same thing apply to charges. If you have Fe is k q q r square, what is going to be the potential energy? Potential will be minus g, not g, sorry, k q q by r. Why did we get this formula for potential? First of all, negative because it is trying to oppose the gravitational field of it, or electric field for talking about electrostatics. The formula came from the formula which we have learned in 9th grade about mgh, potential energy. What is h? R. If you take h to be r, and g is gm by r square. Gm by r square into r, we get the formula. And negative for the opposing the force. So that's where we get the formula. Actually, it is opposite, but I think you guys know the mgh formula first, so that's why I'm explaining it that way. Now, this is the formula of potential energy. Now, if you substitute the value, for example, let us take radon. sorry, radium. Why am I like moving on? Radium. Radium is an radioactive isotope of like the radioactive isotope of radium. So potential energy to escape radium atom for alpha. This is alpha particle, sorry, not radium. And the pit is radium nuclei. Okay. Now the energy to escape this will be minus GMM by R. GMM by R, yes. Sorry, it will be minus KQQ by R. So K, it's constant, so we don't care. What is capital Q? The charge of the radium nuclei. What is the charge of a radium nuclei? It is same as the number of protons present in the radium nuclei, which is 88. So let us put the value 88 E. Charge of an electron, positive part. You know that electron charge is a negative 1.6 times 10 to the power minus 19 coulombs, while the proton is 10 to the power 1.6 times 10 to the power negative 19 coulombs. So this is a sign difference. Alpha particle is 2 electrons, like same as that, but in positive charge. So you understood the thing. Divided by R, radius of the radium nuclei. It is 7.14 times 10 to the power negative 15 meters. If you solve this, you will get the value of let us take it to be more. So 25 mega electron volts. Electron volts is the unit of energy, if you don't know. Approximately equals to 10 to the power minus 18 joules, I guess. Approximately, okay, not exact value. So we got it as 25 mega electron volts. Okay, now let me erase this. Okay, this is the nuclei. Okay, this is after the nuclei, post nuclear part. So if, for example, if I show it like this is the alpha nucleus. This is nucleus, this is alpha particle. If it escapes, then we can just find it. Now, after some while waiting, we found out that alpha particle is here, and then we can measure the kinetic energy, the energy conservation law. How much potential energy is at the top, the same kinetic energy should be at the bottom. Energy conservation. And then after finding the kinetic energy, the energy of this alpha particle must be 25 mega electron volts. Wrong. It came out to be 4.9 mega electron volts. You might be wondering, what? This is the baseline to escape, 25 mega electron volts, and this dude just escaped at 4.9 mega electron volts. Isn't that crazy? Like, how? Like, literally, if you just do it, keep on throwing like here, it won't escape, it will just keep on oscillating here, inside like this. How did it even escape it? Unless this alpha particle had a shovel, and I mean not literally, but figuratively, and dig a tunnel in it and escaped it at the same energy level, 4.9 mega electron volts. Let me just make it like this. And then it just escaped through it without touching the mark of 25 mega electron volts. And guess where the name quantum tunneling comes from? The same phenomena, quantum tunneling, is the reason why this thing gets here. I mean, alpha particle does not build a tunnel because of it for escaping. I've explained you before the probability and then the Heisenberg's uncertainty principle. So when it is at 4.9 mega electron volts, it has 3 states, here, here, or here, somewhere here. Now it has a low probability to reach here, high probability to just reach here, and then here. So after waiting, we get it here. Yeah, that's Heisenberg's uncertainty principle, and that is why quantum tunneling happens. Oof. Now we have a formula to explain like what is this energy coming from, and the formula is and the formula is Q equals to this charge, or the energy, sorry, not charge, mass of the parent nuclei, the original radium nuclei, parent, minus mass of daughter, not new and daughter. After the alpha decay, the remaining atom minus mass of alpha particle, and then you get this. Try solving it for this. You get the values in joules converted into electron volts. The value you get for radium is 4.9 megaelectronvolts. That is why quantum tunneling results in this radioactivity. Now, if you know a little bit about probability, as quantum mechanics is about probability, if you stack up probabilities, it increases. Like if you wait for a long period of time, it increases. So let us wait for 16,000 years. What we get? Half of the radium atoms, radium samples, like literally, escape. Like the alpha particle happened, and the radioactive decay happened. Wait, isn't this time period similar? Right, because 16,000 years is the half-life of radium. That is why 16,000 years, the probability scales up to 50%, where 50% of the atoms degenerate into alpha particles, like in the daughter nuclei, finish causing the alpha decay of half of the sample. That is where half-life comes from. Probability, pure probability. And then I think so this disproves Einstein's idea that God doesn't play dice with us, because as I have already mentioned, don't tell God what to do with his dice. So let us continue with the second thing, sun. How can this thing does do something with the sun? You must know what does actually keep the sun alive. Nuclear fusion, right? Now if you have like the same potential well, the energy well for hydrogen atoms, okay, and let the hydrogen atoms be here. For example, let me just make this like this. Guess the temperature required to do a fusion. Give me a wild guess. The answer is 10 to the power 8 Kelvin. Okay, around approximately. But here's a surprise. The core of the sun at a temperature 10 to the power 7 Kelvin. Like 10 times less temperature. Like literally. How does it come? Like if you come like this and this and then this and this, fusion happen. How in the world at this energy level does the hydrogen atoms fuse? The hydrogen atoms fuse. Tunneling. Here, the Heisenberg's uncertainty principle takes place, and then at a certain probability they reach here and then fuse. Simple. Oh my god, this effect is fueling Earth's core, Sun's core. That's the reason we have life on Earth. Like literally, quantum tunneling means life on Earth. That is why this phenomenon does, require Nobel Prize 2025 this year. 3 physicists, John Clarke, John Martinis, Michel Devoret. Yeah, I hope I pronounced it correctly. Got the Nobel Prize in physics to perform a macroscopic quantum tunneling in circuits. So it is very this is the part where you guys are interested in, because this is where we're talking about this year's Nobel Prize and how did the scientists perform macroscopic quantum tunneling. So let's get started. First, you must know before understanding this, we have only one concept, which is superconductors and Cooper pairs of electrons. So if you have a substance, okay, which is non-magnetic, non-conductive substance. I mean, it is conductive, sorry, but it has a lot of resistance. I mean, like if you have a copper wire, resistance is high, not as high as wood insulating, but high enough to cause a few problems, like a decrease in voltage and other stuff. But if you bring down a temperature to approximately 1 Kelvin to 4 Kelvin, your metal turns into a superconductor, which has literally almost zero resistivity. So, at that temperature, they perform an experiment. Okay, so yeah, and then at that superconductor, the electrons are not like, they're not causing resistance because they're traveling in a pair, Cooper pairs, which means that, let me just write it here, Cooper pairs. They are pairs of electrons which are traveling together without causing any resistivity, almost no resistivity, nothing is perfectly normal. Okay, now what they have managed to achieve is, if you have a loop at two junctions, okay, this is an oversimplified diagram of it. These are known as the Josephson junctions, which means this is Josephson junction, where you have a tiny insulating slip, okay, which doesn't allow any electrons to pass through it. And then we also have a detector, I guess here, squid, not the squid game, superconducting quantum interfering device. Let me write it here, the full function I write. Conducting quantum interfering SQUID. Okay. Now, what a squid does? Squid detects the change in magnetic field. Like if I'm oversimplifying it, if I'm describing it in an oversimplified way, it is measuring the tiny changes in magnetic field caused by electric current. Now, how can electric current pass through this barrier if there is no conduction? This is very superconducting wires. You have Cooper pairs here. The Cooper pair is here. How is it traveling through here? And then how is the circuit getting completed? How is it getting completed? We have barrier. We have two quantum particles, two currents. How is it getting completed? Guys, tell the task. Quantum tunneling. Quantum tunneling causes this to boom. And then the particles are here, and then because of uncertainty principle, it comes here, and then it gets ejected. Oh my god. And then one more thing is that, that why magnetic fields? Because electric currents, magnetic fields are related. Maxwell. First, I think this third or fourth equation of Maxwell, fourth equation describes it well. Even third equation describes it well. That if you have a colloid, I guess. No, not a colloid. A loop of current here flowing, but it is not connected to a circuit. If you have a magnet, if you have something like this, change in magnetic field causes electric field, and then this causes the bulb to light if you have a bulb on it. And this is what is explaining here. Electrons are magnetic because they are charged particles accelerating magnetic field. They are detecting magnetic fields here. Why? Quantum tunneling. This is macroscopic because circuit. Before we could have achieved in small tiny particles, but now we have achieved in literally, oh my god, this is literally achievable. Literally in a circuit, a whole circuit. This is known as for instance, this is known as Josephson current, which is passing through it. So achieving this at a circuit level helps us to build quantum computers, and that is why I think these people got 2025 Physics Nobel Prize. I hope you have understood the concept clearly, and then this topic is not that exhausting as you think, because it is as simple as the normal momentum force and all that you learn. It is the curiosity in you that forces you to learn those concepts. So till now, bye bye. If you have any other queries, type in the comment section, and my next video will be about atomic structure. Okay, which explains quantum mechanics in little depth about SPDF and all that stuff. So till then, stay tuned. Goodbye.